So PurrNet finally got prediction. Now, just as a quick heads up, at the time of recording this, which is the end of January, PurrNet is still in early access, which means paid members have access to it, and it will come out free once it's ready. That being said, you can still easily try and see what PurrNet can do. It's very, very powerful prediction, and it's very easy to use. We've taken great inspiration from setups like Quantum in terms of basically as easy as programming single player code, and it automatically just works with prediction, except the actual setup of it in Unity is, in my opinion, a lot better. It's not as much as like swimming against the current. So let me show you that. So first of all, let's start completely from scratch. There's nothing in our project. This is just an empty scene. Now, first of all, I'm just going to set up sort of our network manager setup as you normally would with PurrNet. I expect you to be familiar with this at this point. If you're going to be working with prediction, I expect that you are familiar with networking. Otherwise, I can't recommend it. Now, for now, we're going to just take the unsafe rules. And I'm just going to take some of the network prefabs that we already have in the project, just because it doesn't really matter. We're not spawning from this prefabs. Essentially, the predicted setup is completely separate. I'm going to skip a little bit quickly through this. Let's just use the UDP transport just for ease. And then let's make a new game object here that we're going to call the prediction manager. And essentially this is what's going to be handling the prediction. So we're going to add the prediction manager object to it. And we can choose what provider of physics do we want, if any. BPU physics is our external physics. That's of course Unity Physics 3D and Unity Physics 2D. In my case, just to show that the prediction works, we're going to be using Unity Physics 3D. Now, cool. This prefabs list is for now how we handle the spawning of prefabs. This will be similar to sort of the network prefabs and stuff, but as I mentioned, this is just an early access preview, and people who are paid members will have access to this already, be able to play around with it and stuff like that. And of course, in the Discord channel, there's the early access channel where you'll be able to see all the information on how you download it and some of the heads up of things that we already know that we're working on fixing. But we really just wanted to give you guys some early access and be able to play around with this. So let's make a completely empty game object now, and let's call this our player. Right, I'm going to put this in 000. I'm going to go to scene view here real quick. We're going to move the player out here. And let's move it, let's say 1 up. Now let's give the player a body as well. So let's go in here and let's just give it a sphere so it can, roll around, and this will be the body. This is essentially, well, we can also call it the visuals, the graphics, whatever you want to call it. I'm just going to call it the body. Now the reason for this, and it's very important that you set up your visuals externally from your player, is because the way that we do it is similar to Quantum in the sense that we sort of simulate everything that's happening separate from how we handle the visuals. This essentially allows you to separate the two logics. So a lot of stuff, a lot of jitter, a lot of things like this can happen behind the scenes, but outwards towards the player, it will be fully smooth and it will be a good experience. Let's start by adding the predicted rigid body component, which will automatically have added a few things. It of course added the normal rigid body, it added the predicted transform where we have to drag and drop our graphics in, and it added the predicted rigid body component. So now that we essentially have these, this is now pretty much a predicted object. Now when it moves around stuff, it's predicted with physics. Now let's make a script for this, and this will just be, let's say, our player movement. And let's drag and drop that onto our player as well once it's done compiling. There we go. And now let's try and open this up, and let's just look into how you program with our prediction now. So there's a few things that you need to know. First of all, the most important thing is the idea of the predicted identity. The predicted identity is essentially our network identity, but for prediction. So as I mentioned, it runs completely separately. So you shouldn't be mixing the two. When you work with prediction, you work with prediction 100%. And that's how it should work. And that'll essentially keep consistency throughout your game. A normal predicted identity like this can, handle things on its own. But for our player, we essentially need some kind of input and we need some kind of state as well. And just to show you behind the scenes, how a predicted identity that only has a state, so for example like the predicted rigid body 2D, or for that sake the predicted rigid body that's not 2D, same thing really. As you can see, this is just a predicted identity and it just holds a state. There's no input in this because this is not about moving it, this is just about syncing, like the velocity and whatever we want to sync. In this case, you can see that we have some Unity rigid body state, which is a thing of its own. And you can see that just keeps track of the linear and angular velocity. And that's essentially the things that we want to sync in this case. And that's pretty much what handle, right? So when we get the initial state, we get the rigid body linear and angular velocity. Let's also get and set Unity states and so on. I would really argue like look into some of these examples that will already be available to you. We already have some movement and examples already of like also spawning cubes and shooting them around, stuff like that. But what we need is ours needs both an input and a state. So let's go and make that. We can just make it here outside our class, and I'll make a public struct. And this will essentially be, let's make it our player input. Now this needs to inherit from our predicted data. Like so. And we also now need to make a public struct for, this will essentially be our player state. And this will also be our predicted data, but with the type of the player state. So just like this, we've now set them up. Now up here, I believe it is the state first and then it's the player input, if I'm not wrong. I might be wrong. I think I inverted them. It's the player input and then the player state. Yeah, there we go. And now we can just implement the members, which is get input and simulate. So now that we've implemented these members, this is essentially where we have to handle most of our stuff, right? So just to firstly clarify, when do you use a state, when do you not, and what is the input and so on. So going through it very quickly, first of all, the input, that's very simple. You essentially just get the input as you would here. So in our case, we can just make var input equals to new, and of course this will be new of the type player input. And here we can then say, the horizontal is equal to input.getAxis raw, and then this will be the horizontal axis. And we'll just do the same thing for vertical. And you can't exactly do the same thing for jump, and I'll go over that in a little bit. And then here we just return the input because it's expecting the type plane. But that's it. Now we've handled input. And now you notice here in our simulate, let me just put the input down here at the bottom because that's how I like it the best. Now you'll notice here in our simulate, we get in some input, we get in a player state, and we get in a delta. And this is essentially all the information that you should be simulating the player with. So simulate is essentially what handles the actual simulation of what's going on in the game. This is what I talked about. So essentially in the game, in the background with prediction, how prediction works is it'll run on your tick rate, right? So for example, in our case, if we want it to be very smooth, we can set a tick rate of 60. And then our player, when for example moving to the right, will 60 times a second be lagging pretty much to the right, like. And that will be what's happening behind the scenes, because it'll be simulated then at 60 FPS. If we had 10, it'll essentially be simulated at 10 FPS a second. Or well, 10 frames per second. And the visuals, that's what's handled pretty much with the predicted transform, is it'll just automatically interpolate the visuals for you. And we'll get into that a little bit too. So essentially in simulate, this is where we're handling what's happening in the simulation. This has nothing to do with visuals. You shouldn't be handling visuals here. This is where you should be handling functionality. So for example, we want to move the rigid body. Now we can serialize fields, like for example the rigid body, which are things that aren't going to change. So our rigid body, for example, is not going to be changing. It's not a dynamic number. Whereas for example, if I made a private float, like a jump cooldown timer, for example, that starts from 0 and counts up, we shouldn't have this here. This should be part of the state, because the state is what reconciles properly, essentially going back in time, replaying, checking everything aligns, and making sure that anti-cheating is in place and everything aligns as it should with prediction and physics work and so on and so forth. There's a lot of reasons for it, but essentially anything that's sort of fixed and already set, you can just fine have in Unity editor, like for example our rigid body, because that's not going to be changing dynamically. But if we had something that were to change dynamically, we'd have that in the player state. Again, for example, if you wanted to jump cooldown or something like that. Going into our rigid body here, let's just do, for example, let's add a rigid body force, or actually we can just set the velocity, right? So we can essentially just do this. So rigid body velocity will be equal to new vector 3, depending on the horizontal and vertical velocity. And we can of course also have some kind of speed field. So private float speed. Again, this is not going to be changing, so this is just going to be how fast are we moving. So we can just times that with our speed, and this should pretty much work. And again, this is linear velocity. Another thing is our input has this little question mark, which means it's nullable. That means we could potentially get no information here. And just to safeguard that, we'll just do if input.value, if input.has-value, we return, and we've got to invert that, of course. So if input does not have a value, which means it's not valid, then we return. Now you can see that the lines here disappeared. And this is basically it. As you can see, it's as easy as that. We took the input, we just make sure there is some input, and then we use the input how you want. And this is I promise you, this is it. This is all that you really have to do. Now, right here, we're setting the linear velocity actually. So realize if we want to add jumping and stuff later, this is a bad way to go about it. So let me actually just refactor this. But it's really as easy as just moving, right? So we can just do add force, and let's make a new bar of our move. That'll be our new vector 3, which will take in the input.value.horizontal.x, horizontal, and we'll also take in the vertical. And of course, we can now also normalize this just to make sure that there's no funky business going on. I guess technically you should be normalizing the input. This is fine. We don't need to normalize this bit. We can add force of the movement, and we can add the speed. And that's pretty much it. Right now we're moving with force. Right, so now let me move the player movement up here to the top. We'll feed it its own rigid body. And that's really it. And now, of course, let's make a prefab out of it. So I'm just going to drag and drop it in here. We need to give that prefab to the prediction manager so it knows to spawn it. Again, this is just an early setup of it. And then we also do have a player spawner, not this one, a predicted player spawner already in here that you can use. Can give some spawn points. So let me give spawn points. Again, these components will be made a bit nicer and stuff in the future, but for now we really just wanted something up. Just set the camera up so it's like up here looking down already. So that is already ready and set up. And then let me add these spawn points like so. And let me hit play. Now you can see I can move around. And I can assure you this is predicted. It's really as easy as that. So let me open up my clone and we load that up. And now let's hit play and hit play. And now the clone is spawned. And as you can see, these can now interact, and we have physics interactions. They can push each other. They can both move at the same time and hit each other. They can interact with the same objects, as long as the objects are predicted. And yeah, these things will really just work really quite well. So yeah, that's as easy as that. Now you have predicted movement. Now let's set up the jumping just so you can see how that's a little bit different. Because we can't just do jump equals to input.get key down key code dot space. We can't just do that. Now I wish we could, but the thing is this get input is only happening on tick, right? Which means it's only getting input. Let's say if you run 20 ticks, it's only getting input 20 times a second. With 60 ticks, it's getting input 60 times a second. However, the get key down value only triggers on a frame, right? Which means if you're running 500 frames but 20 ticks, there's a very high likelihood they're not going to hit at the same time. So what we do need to do is we do locally have to store whether we want to jump. So we can say underscore want to jump, for example, as a bool, and then we can open up the update method and then we can check our input there. So I can just do if, and then we can get this input.get key down key code space. Then we can say want to jump equals true. And now what we can do here is we essentially just give it the want to jump. And then before we return the input, we just always set want to jump back to false. And that's as easy as that. Now this is essentially sort of a toggle, right? So when we click space, it just says, hey, I want to jump on the next tick. And then on the next tick, it uses the jump and sets it back to false. So you can click it as many times as you want, but it'll still remain true until it's used, if you know what I mean. So now when I click here, oh, of course we didn't implement the jump. So now let me do if input.value.jump, and then do rb.addForce. Let's just do vector3.up, and let's just do some kind of jump value. Let's do 10, and then we do it of the force mode of impulse. And there we go. Now we added a jump. Again, this is as easy as just writing single player code, basically. And now we should see a jump, and it should look smooth and good. So let me start here, and when I hit space, I jump. And you can see now the clone joins. He can move around, I can hit space and he jumps. And they can interact, physics, they can land on each other. Like for example, I can have him jump up here and I can try and see if I can hit him, but I could not see depth at all. Let's try and align that just so you can see that it does indeed work, you know, with multiplayer. So let me try and have this guy like move left here and then this guy jump into him. There you go. You can see they collide in the air, they can hit each other on the way down. Like things just work, it's fully predicted. And that's really the beauty of such a simple system to use. Now let's say we wanted some kind of cooldown, right? Right now we can, let me also make that a little bit lower. Now, right now we can jump as much as we want. We can jump all the time. And I don't want this. I want a jump timer. So let's do some kind of serialized field, private, float, jump, cooldown. And this will be 3 seconds, for example. This essentially means now we need a timer in here. So in the player struct, we can make a public float jump timer, for example. Something like this. And what we can just do is every time that we simulate, we can just do state.jumpTimer plus equals to our delta. And the thing is, the delta is a fixed point. So that means right now we have to cast it to a float because we're working with floats. We are going to have deterministic physics and stuff implemented. That's the other physics system, but it's not fully in there yet at the point of recording. But of course, this is just so we can have completely deterministic math. And now this is as easy as that. Now we're counting up the jump timer. What we essentially have to do now is we just check if the jump timer and jump timer is greater than or equals to the jump cooldown, right? But let's say, for example, now let's go and test it, right? So if I do now, when I hit play and I try and spam space, so now I'm just going to spam space, I can't jump before 3 seconds have passed, and boom, there we go. Now I could jump. And you can also see now when I jump, actually, I could jump infinitely because we forgot to reset it. So let's set jump timer back to 0, like that. So now we essentially have a jump timer of 3 seconds. However, as I mentioned, I can't jump for the first 3 seconds, but I want to be able to do that. And what we can do is we can get the initial state, like so. And with that, what we essentially want to do is we want to make a new initial state. So new player state, like so. And this can now have the jump timer be set equal to the jump cooldown from the very beginning, like so. And then we just return this initial state. And the reason why this works is obviously because now when we start the game, it'll get the initial state, and the initial state will be as high as 3, which means we can now immediately jump. So this is how you would set sort of any initial values that you wanted inside the struct. And again, this works predictably as well. So now when I hit play, I can jump, and I can see I spam space. I can't jump anymore. keep spamming space, and there we go. Now I could jump after 3 seconds again. Now I can't jump, and there we go. And here I hit space again. And same obviously goes for the client. So it's as easy as that. You pretty much just program it, you know, almost just as you would locally. The only thing that's really different is you of course want to handle the input a little bit differently, as like through a struct. But that's mostly it. You get the input how you want to get the input. You work with it pretty much how you want, except for this line. Pretty much all of this logic here is as you would expect local code to work, right? Even if you had like a local jump timer out here, that's pretty much how you would expect it to work. So yeah, hopefully this makes sense. And the last thing I wanted to show you is just some of the sort of settings that you can play around with. So on the player, especially on the predicted transform, you can see there are some interpolation settings. And you can change these as you want. Essentially right now they don't have that much going on, and they probably won't in the future. But essentially you can play around with these because it's gonna depend on the type of game, right? If you have a super fast-paced, high-paced, high-octane game with a lot of extreme collisions, you might want to make things, you know, smoother over time and take longer to blend or whatever. Or let's say you have a super high precision game and it's extremely important that all visuals align, well then you'd probably want to make the corrections a lot harsher and have less leeway and stuff like that. So for example, you could have the blend rate way higher and the blend difference way lower and stuff like that. And essentially you could play around with these as you want, and as you can see, like rotational interpolation, positional interpolation, these all work well. And we actually have an example scene in here already in the setup you'll have access to, where we actually do play around with rotations. You can see here we have 100 ping because we're emulating it on sort of the slow relay server we have. And you can see it works really well with rotation stuff. Obviously, in this case, I'm the host, so things will always look really good. But you'll have examples to play around with. And here you can also spawn cubes with space. And you can also look into how that all works and stuff like that. So, really cool. Yeah, I hope this was helpful. It was really just a quick introduction. Of course, there'll be way more videos on prediction in the future and how to use more exact examples and stuff, but we really just wanted to give kind of a heads up, a quick start. You can see what we're working on behind the scenes and also what you can have access to already if you're a paid member in the PurrNet Discord. So yeah, let me know in the comments as well what other kinds of prediction projects you'd like to see in the future. If you'd like to see a competitively viable shooter or a smash kind of fighting game, or what you'd really like to see, and I'll of course work on that behind the scenes. So thank you very much for watching as always. Please do leave a like, comment and subscribe. It truly helps a lot. I hope that you have a wonderful day.